result right here tells us a lot about why LU factorization without pivoting is a bad idea. Let's think about this. When we do LU factorization without pivoting, the element on the diagonal by which we divide could be in magnitude very small relative to some of the other elements below it. And when you then divide by that element, you may end up creating very large elements, multipliers, and then you use those multipliers to take a multiple of the current row and add that to another row. Now this hurts us in two different ways. One way in which it hurts us is that multipliers being small translate to elements of our computed matrix L being very large in magnitude. So now we end up with an error bound where some of the entries in this matrix right here could be very large in magnitude. Not so good. Worse, when we take a very large multiple of a row and add it to another row, we may end up creating very large entries in our computed matrix U. And then we take something that may have very large entries in it and we multiply it times another matrix that may have very large entries in it. And now we've taken the absolute values of those entries so they can't cancel each other. And we may end up with very, very large bounds in the end. What does that mean? That means that this matrix, that is the change that we see in matrix A, which is due to error that has accumulated as part of our algorithm, could be very, very large, which then could mean that we're actually solving a completely different linear system. Not so good. Now, what did we say we should do instead? What we said we should do instead is take our matrix A, perform pivoting as we perform our LU factorization, and what we said was, well, that's equivalent to saying we know how we should rearrange our rows, and then we should compute our LU factorization of that. Now, whether we do that on the fly or whether we permute a priori doesn't change the computations that happen, and therefore this L and U have exactly the same error bounds as we get right here, except starting with the permuted matrix. So what we get is actually this result right here. Okay? And then you can take that L, well, then you can permute the right-hand side. Remember, we're trying to solve AX is equal to Y, so now we can permute both sides in the same way. Well, permuting, rearranging the vector, that doesn't involve any error being introduced because that's rearranging entries. Okay. So, the bottom line is that when you incorporate row exchanges, you actually solve the exact linear system as if you have permuted it ahead of time, where the error that is introduced in matrix A is now bounded by the same bound. And you say, well, that means we're no better off than before, except when we permute, we're inherently putting the element with largest magnitude on the diagonal so that we then divide by it. And if you think about it, what that means is that all of the elements in L are in magnitude less than 1. Good. The other thing you realize is, oh, wait a minute, now I'm multiplying the current row by a multiplier that's no greater than 1 in magnitude, and therefore I'm not adding something that is hugely different from to any particular row than what was already in the row, and therefore the elements in U probably aren't all that large either. So we get a double benefit. We get that the elements of L are bounded inherently by 1 in magnitude, and the growth that you see in the elements in U isn't nearly as dramatic. And as a result, the bound on the elements in A is much tighter, is much better, and as a result, you have the exact solution to something that is changed much less than it was when we didn't do pivoting. Okay? And all of a sudden we understand pivoting much better.